Hello everyone. Today we will discuss an end-to-end project and we will consider a regression task for the same. To be specific, we will see the house prediction dataset. We will try to analyze the features, their different characteristics. We will also see the correlation between them and we will try to implement linear regression algorithm on this dataset as a linear combination of features, but we will also include the polynomial features of those variables available in the data set to develop a better linear regression algorithm. At the same time, we would also like to employ the dimensional reduction technique in order to reduce the number of features, and then we will analyze how it affects the performance on this specific data set. Let's start and discuss about the data set first. As you have seen this data set earlier, it is called California house pricing data set. It contains the details of house prices of California district according to the 1990 census, and it serves as an excellent introduction to implement machine learning algorithms, to be specific, regression algorithms. The objective of this data set to predict the median house value of a given house given the number of features, as we discuss later. It is a very famous and commonly used data set, and when we downloaded this data set from the given link, there were already 136k downloads of the same data set. The data set consists of 9 independent features and one dependent variable or feature called median house value. The total records or rows which are there in this data set are 20,640. So this is the description of the features. We have seen that in earlier videos also, but let's go through them once again. The first attribute or feature is the longitude value. It gives a measure of how far this house is, the specific house is, from the west. The higher the value, the farther it is from the west. Similarly, we also have the latitude value, which gives us a measure of how far the house is from the north. We have the median age of the house, which tells us how new or old the building is. Total rooms within the block where the house is, total bedrooms in a given block. We also have the number of people living around or within a block, and the feature name is population. We also have the total number of households or group of people residing within a single home unit for a block. So the households is there. We also have the median income for the households within a block of houses, and which is measured in tens of thousands of US dollars. And another important feature is how close the given house is from the ocean, depending upon the location of that house. Now, all the features there are numeric in nature. They contain the real numbers, but ocean proximity, it is a categorical. It is based on the categorical values, where the values are like island, which means that this house is on an island or near to beach or 1 kilometer from the beach. And I think there are 5 to 6 categories in this specific feature. Finally, after independent variable, the job then is to, given all these 9 independent variables or features, what is the median house value in US dollars? Right? So we will try to predict this value on the basis of the values of the given independent variables. So this is just a snapshot of California housing prices data set. We have all the 9 features here, the independent variables, and then this dependent variable, which has been shown here in red, is what we want to predict. As we'll see later on also, and you can derive from this snapshot also, that the values lie in different ranges, right? Some are very small, their range is rather small in comparison to the other values like total rooms, okay? And some might be negative also, right? So longitude values are minus 122.23, and the rest of them are, as you can see, they are positive. Also, ocean proximity is a categorical feature here which contains the values like the house is near the bay, it is inland, it is near the ocean, and there are some other categories as well. This matrix here represents the correlation between the features. We will also try to derive the map of correlation between the features when we see the visualization of this data in the Python worksheet. But you can derive a few things like if we talk about the dependent variable, it depends highly on the median income in comparison to any other feature. So this kind of analysis, that which features are related and what is the degree of correlation between them, this information can be gathered from this correlation matrix. We will discuss that in detail later. And this will be the line of process that we will do on this specific data set. We will start with the visualization, where we will try to make sense of the basic features, basic statistics and visualization related to the features, like what is the mean value of individual column and what is the distribution and the correlation matrix and all. Then after loading the data, we will apply some pre-processing techniques. This specific data set actually contains missing values or null values as well for a specific column. So before applying the linear regression algorithm, we need to take care of those null values. So this is a very commonly used pre-processing step. Linear regression is a type of algorithm which is affected by the range of values which are there in the column. So applying a standardization technique as the pre-processing step often helps in prediction. Then we'll try to apply linear regression algorithm. We'll do two versions. First, we will just take a linear combination of all the features and will not consider any polynomial feature or higher order polynomials. But later on, we will also try to add 2-degree polynomials of the given feature and see whether it improves the performance of the prediction. Finally, we will also try to apply some dimensional reduction technique on this data set, and then further we will try to apply linear regression to see, after reducing the dimensionality, what is the impact on the performance of the linear regression algorithm. So we'll try to cover all these points in Python worksheet. So this is all about the basic introduction of the data set. Now let's jump onto the Python programming and let's try to implement all these steps one by one. So welcome to the visualization of house prediction data set. I have already mounted my drive where I have this data set available. Now let's import the data set from the drive. So I have extracted the data set from my drive also. Let's discuss some basic information of this data set available in the data frame D app. As you can see here, as the first information, there are total 2640 rows or house information is there, ranging from 0 to 20,639. Overall, there are 10 columns. If you look at the index, it starts with 0, goes till 9. So there are 10 columns overall. The last column here, median house value, is something that we want to predict. The second column, or rather the third column here, shows how many values in each column are not null. So all of them are completely full except total number of bedrooms. So there are we have some missing values. Then we also have the type of data it contains. So some of them contains real number data float, some of them contains integer data, and some of them, in fact one of them, is of type string, as we have discussed, ocean proximity. Apart from that, we can also fetch some useful information or basic statistical measures for each column here. So for all of them, the count is mentioned, which we have already discussed. The mean value is mentioned here for each of the column, the standard deviation, the minimum value of that column, the first quartile, which is represented as 25%, the median, which is represented as 50%, and the third quartile, which is represented as 75%, is mentioned there, and the max value for each column is also there. So for example, for housing median age, the total values which are not null are 20,640. 28.63 is its mean value for this column. 12.58 is the standard deviation. 1 is the minimum value for this column, which represents that there is a house in this column which is only 1 year, or that block is only 1 year old. Then we have the first quartile median value is 18, median value is 29, third quartile value is 37, and the max value is 52. Means the maximum, the oldest house in a block is 52 years old. And the similar statistics can be easily observed from all these columns for each features. Then we can also plot the histogram and the density estimation curve for each of the column. We can also design, or rather print a graph with multiple columns at one figure only, but we'll try to do one at a time. So in this specific case, I'm drawing the histogram for house median age. So total bins here are 50, and the color we are using is green. So as you can see here, the overall data is divided into 50 bins, and the last bin here, 52, seems to have the highest number of values, which is represented with this very big vertical line here. And we can also see the density estimation curve here, kernel density estimation curve, KDE, which goes like this. Similarly, we can plot the histogram for other columns as well. Let's try some other column. Let's say median income. So if we change the column to median income, and we will keep the same number of bins here, then we will see that the curve of median income looks like this. So it is more normalized in comparison to the previous curve that we have seen. Now let's move forward and discuss the correlation between the variables. It gives us this matrix, and you can see here, as we have observed earlier, that if you talk about the target variable here, which is the median house value, then median income has the highest correlation with our target variable, 0.69. But apart from that, you can see that there is some serious correlation between different independent variables. For example, if you look at here, 0.93, this represents the correlation between total rooms and total number of bedrooms, which makes sense. The more the rooms you have, there is highly likelihood that the number of bedrooms will also increase. It's a very strong positive correlation. There is a quite high correlation between total number of rooms and population also, which is 0.86, which once again makes sense. When you have lots of rooms in a block, in a house, then the number of population living in that block is going to be more. Similarly, there is a strong correlation between total bedrooms and total population, total bedrooms and total household, quite high correlation, 0.98. So this block in between, which represents the relation between total rooms, total bedrooms, the population, the households, this block is highly correlated with one another. If we talk about the target variable, some of the variables have negative correlation also, though it is very small, but longitude and latitude, it shows the negative correlation with the target variable. Also, the population shows the negative correlation with the target variable. Once again, really small, and median age of the house and total room, total bedroom, number of household, all of them are positively correlated, but the degree of correlation is really small. The only one which has the highest correlation, the strong positive correlation, is median income. So this kind of analysis can be done with the help of the correlation. It is also observed that for better prediction, the features which are highly correlated with one another, we should consider only one of them. So let's say two independent features have high correlation among them, then we can actually drop one and can use only one of them, right? So this type of analysis and further processing can also be done on the basis of this correlation information. So this is all about the visualization of this housing data. Now let's focus more on how we can apply different pre-processing steps on this data, and then how we can use linear regression to predict the value of median house. Let's do it now. So welcome once again on this house prediction task. Once we have understand the data and we have visualized the basic features in the correlation matrix and have gained some useful insights into the data, the next step is now to implement the linear regression algorithm on that. So I have already mounted my drive, and let us import the necessary libraries. So here we are using the pandas library, the numpy library to do the matrix operations. We have used the model selection of scikit-learn to use train and test split function. Since ocean proximity is contains categorical values, that's why we are using the label encoder also, which will convert the given value into some numeric number. Then obviously out of linear model of scikit-learn, we will be using the linear regression module, and as a performance matrix we will use mean squared error and R2 score. So let's import the libraries first. After that, we will upload the data. Let's view the data. Now, as you can see here, once again, we have 9 independent variables and 1 dependent variable, which is median house value. To confirm, let's check the size of the data once again. So, as you can see here, the data is the number of rows are 20,640 and 10 columns overall, including the dependent feature column. As I told you, ocean proximity it contains categorical values. So we can see that there are only 5 entries of the houses which are on the island. 2,290 houses are nearby, and so on. But overall, you can see here that there are 5 different categories which are there, and they are categorical in nature. Obviously, linear regression cannot be applied directly on the categorical data, so we need to first convert that into the corresponding values. We can do that easily with the help of label encoder. It assigns an integer number to each separate category. So if we compare this data here with this data, now you can see that less than 1 our ocean is represented with 0, inland is represented with 1, near ocean is represented with 4, near bay is with the number 3, integer 3, and island with the integer 5. So what we have done is we have converted the categorical value into integer values, which is now suitable for linear regression to be applied on it. Once again, we have added this new information in the form of a new column with the name ocean proximity encoded. The next part is we have to check whether there exists null values there or not. For that we can use the is null functionality of data frame, and if there are any null value there, it will tell us. So if we run it, you can see that for each column it is telling us whether that column contains the null value or not. So longitude does not contain null value and so on, except total number of bedrooms. So its value is true. Okay. Now before feeding this data into the linear regression model, we will apply the pre-processing technique for, first of all, to remove the missing data to fill it up, and then secondly we will also apply the standardization. Let's do it one by one. So once we fill the null values with the mean value of that column, right? So if you run it, so the null values have been replaced with the mean values of that column. Let's check whether the data contains null values now after this pre-processing step. We can see that now total number of bedroom does not have any null value. Right? So the value turns out to be false. Then, since we have already encoded this column ocean proximity, we can remove it. We have converted this ocean proximity into ocean proximity encoded column. So we can remove this categorical column from here, and we are calling it the clean data now. Once we have done it, the next part now is to set our matrix of independent variables as x and the vector which we want to predict as y. We have done it many times now when we are discussing the machine learning as well as deep learning task. Now before once again feeding the data into the linear regression, we will apply the standardization process on it, and it will convert the given data into mean value to 0, and the standard deviation of that specific column should be around 1. Why we do that? Linear regression is one of the algorithms that is very sensitive to the range of data that it contains. So if we apply the standardization process, it brings all the columns into similar range and hence often improves the performance of linear regression algorithm. So let's apply this, and we can also check that all the values are now within similar range. Then the next step is to divide the data into training and test set. Here we are considering 10% of the overall data as the test set, and rest of that will go as a training data set. And we are also printing what is the shape of training and testing data set after splitting the overall data set. So we can check the training data set now this time is 18,576. It contains 9 columns now because we have removed the dependent feature, that is house value, from this X data only. Now Y data contains, Y train contains that information. And similarly, test set is the 10% of the overall data set. It contains 2064 instances. So what we'll do now is we'll create a linear regression model. We are calling it LR. LR stands for linear regression model, and then we will feed it with the training data available with us. So we have created this linear regression model. The next step then is first check the accuracy of this linear regression model even on training data. So we will first apply the set of independent variables. We will get the predictions for training data, and then we will compare that with the actual predictions. For that, we are using the mean squared error. Actually, we are calculating the root mean squared error. So if we set the squared parameter as false, it gives us the root mean squared error, and it is useful because mean squared error, it calculates the square of the error. So if the difference between the two entities is relatively large, then its square becomes even more large, right? So to reduce it, we often prefer calculating root mean square error as well. Lastly, we will calculate the R2 score also on the actual training values and the predicted training values. So when we do that, we can see that this is 69,270 is the root mean square error on training data set, and this is the R square value, which is close to 0.64. Now, if we are satisfied with this performance, then we will proceed and test the performance on the test data set. This time we are passing the test set, and it will give us the predictions related to test set, and then we will compare that with the actual values for that test set. Let's run this and check the results. So in this case, the amount of error has increased if we compare that with the training error, and the R value or R square value is decreased in comparison to the training R square value. And this is a common phenomenon that usually in training you have the high performance, and in testing you have a relatively low performance. Now, if we are satisfied with this performance, we will stop. But if we are not satisfied, then there is a requirement to change the model. So what we can change in a linear regression is that we can include higher order polynomial terms. Let's say we want to add the 2-degree terms in that, which means that the squared values of all the features and their multiplications, which are of order 2, will be calculated and added into the data. For that, we will use the inbuilt functionality which is available in the pre-processing module of scikit-learn. It is called polynomial features, in which we will just pass of the degree of polynomials that we want. In our case, degree is 2, as you can see here. And when we pass our matrix of independent variables to it, it will calculate the corresponding polynomial features of degree 2. So let's run it. And let's check the shape of this polynomial vector matrix. So in this case, you can see that the number of rows are same, but the number of columns now, or independent variables now, have increased from 9 to 55 because we have calculated the squared or a second degree polynomial, all the possible combinations of them. Now, using this polynomial matrix of features, we will once again split our data into training and testing, and we will continue with the rest of the process. So this is the training. This is the train and test split. We are keeping the same distribution, 10% for testing and rest of that for training. Then we once again create a new linear regression model. We are calling it linear regression for polynomial. We have passed the newly created training data to it, and then once again we will calculate first the predictions on training data, which gives us values like this. So as you can see that the error has decreased and the R value on training data has increased. In fact, if you remember earlier, it was around 0.64. but this coefficient of determination has been increased to 0.7. Now let's check the performance on testing data this time on using polynomial features. So we have calculated. Let's print that. So once printed, the value has slightly increased for r square and slightly decreased for the error, but the margin between the previous case when we were not using the polynomial features and this case is not very big. So this is how we proceed. We train a model, we check the performance on training and testing data. If we're satisfied with the model, then we go ahead. If we are not satisfied with the model, then we'll make changes into the same model, or maybe we will use a different algorithm altogether and check the performance on that algorithm. Maybe in this specific case, we can also utilize artificial neural network for regression and compare that with the performance of the linear regression models. Now let's implement the linear regression once again, but this time by incorporating one more step of feature extraction, which comes under the umbrella of dimensionality reduction. If you remember, feature extraction refers to the fact that given the set of independent features, we generate new features out of these original features. That's why we name feature extraction. Usually, the number of extracted features are less than the set of original features, which helps us reduce the dimensionality of the total data and improves the running time. And sometimes it also improves the performance. So, while we were discussing feature extraction, we discussed a very famous algorithm called principal component analysis, or PCA. We will be utilizing the same in this particular example. So let's first the library. Then we will use the data, clean data once again to create X and Y once again. We will apply the pre-processing step of standardization, and then we will apply PCA to it. Once we will pass X to it, the PCA dot fit transform function will apply the principal component analysis algorithm to it and will give us the extracted feature. We are calling it X underscore PCA. It is also important to note that how many principal components you want to keep it, right? So in this specific case, we are keeping only 6 components. We are reducing the dimensionality from 9 to 6. So when we apply this, it gives us XPCA, and using this XPCA, we will once again split our data into training and testing. We are maintaining the same distribution, 10% for testing, the rest of the 90% for training. When we run it and print the shape, you can observe that now the number of columns are not 9 anymore. They have been reduced to 6 since we have applied principal component analysis. We are keeping only 6 principal components out of all the possible components which are there. Once we have reduced the dimensionality, the rest of the process is same. We can apply the linear regression, but we are using the simple linear regression. We have not included the second degree polynomials to that. So when we run it and fit the data by providing the training data set, next step is to check the performance on the training data set first. So as you can see here, the performance is not better when the number of columns were 9, and this happens when we reduce the dimensionality, and we might lose some information in the process also. But as using PCA, as we increase the dimensionality once again towards the original number of features, chances are that the performance should improve. But let's first test the performance on the testing data also, and it is also worse than what we had when we were using the original feature, means 9 features. So if we compare the performance before feature extraction and after feature extraction, we can see that previously the R square value for training was 0.63, it has been reduced to 0.54, and previously for testing also R square value was 0.59, it has been reduced to 0.514. It might happen when reducing the dimensionality also uh, you know help us lose some information that was there in the data set. Now let's try do one more thing. Let's try to increase the number of principal component analysis in our PCA algorithm. So rather than 6, let's say this time we will use 8 principal components. So if you remember, initially the original number of features were 9, we are still have reduced the dimensionality, but the difference is not much. Initially they were 9, and this time we are keeping 8 principal components. Once again, we have calculated the extracted features. We will once again divide the data into training and testing. You can check here that here now the number of features have been increased to 8. Once again, we will fit the data. We will make the predictions on the training data set. So it has been improved actually a little bit. We will compare it further. But first, let's run the testing data set also, and it also has slightly improved. So if we once again, after increasing the number of principal components to 8, increasing the dimensionality from 6 to 8, now let's compare that with and without feature extraction. So if we compare that, the error here was 69 and 270. So in training data, the error has increased a little bit. R square value on training data before, while we had the original number of features was 0.6395. So it has come very close actually to that value also. But you can see that on the testing data, the performance has improved. Before, when we were using the original features, the error on the testing data set was 73,644. But this time it has been reduced to 72,326. Also, if we look at the R square value, it was 0.5933, but it has been improved to 0.6077. Right? So even though we have less number of features, that is 8 in comparison to the original number of features 9, is still the performance on the testing data has improved. So it means that our 8 feature carry all the necessary information that was originally there in 9 feature, and this is how we can apply the dimensional reduction step as well. So this is all about the end-to-end project on this regression task. Thank you.